Okay, next up is Dr. James Bryce. He's going to talk to us about a guide for timing of asphalt preservation.
We're going to dig into some numbers and we're going to look at it. But fundamentally, that whole piece of advice he gave you, it depends, is there. I'll just give you a preview. When should you apply pavement preservation? Thank you. Okay, you passed the quiz. I'll start by saying welcome to my newly adopted home state. We're here, somewhere around there. Right there I live. Not too many people in here had Matthew McConaughey make a great movie about your university, so I'm proud of that. Proud enough that I now drink wild turkey instead of scotch. Welcome, we're glad to have you. It's a beautiful place. If you get to come back here during the winter, or during the summer, sorry, not during the winter. But for some reason, Travis keeps scheduling these things in October and March. It doesn't really work out that way. So what are we going to talk about today? We're going to go through NCHRP Project 1438. I'm not going to reference a report number because fundamentally it boils down to the fact that we couldn't simplify this report enough for publication. I am a big proponent of trying to say, well, pavements are complex systems. And sometimes you actually have to understand the complexities involved with the systems. So as we keep getting pressure to simplify, we want a y equals mx plus b relationship. And we go back and we say, no, it cannot be made that simple. If you want to make correct decisions, it can't be made that simple. So I'm a big proponent of that. So we're going to see that today. This report here, though, is also posted online under the TRB website, NCHRP Report 1438. You can go through there, along with all the models and everything we're going to show you today. We'll go through this. But one key thing I want to point out is this figure here. And this is where the whole it depends aspect comes from. Because when we talk about pavement preservation, we all know what preservation is, right? We've got a couple working definitions, federal highway, AASHTO, they're all out there. But fundamentally what we're talking about is while the road's in good condition, we're going to do something, right? And that something that we do, whether it's a thin overlay or chip seal or whatever it is, likely it's going to have some immediate change in condition. Maybe it won't be. And likely you're going to have some change in performance, right? Or maybe we want to capture that. So in order to understand when we're actually supposed to apply that, we have to understand the behavior of both of those, that initial jump and that change in performance, right? So if I apply a chip seal and I'm concerned with IRI, I'm not going to see that immediate jump in performance. Just heads up, your chip seals are not expected to immediately change your IRI. However, I can expect a change in performance. That fundamentally affects the timing that we'll look at. And again, we know, I mean, these are two, and thank you again, Dr. Hall, two duh statements, something that everybody in here should know. Apply preservation when the pavement's in good condition, right? Don't apply preservation if you've got massive holes in your road. And it's a relatively low-cost treatment. NCHRP Project 1438 was fundamentally about asking the question, or answering the question, but answering the question, when should we apply pavement preservation? And how does that timing change as a function of various factors? You know, your pavement structure, your traffic, your climate conditions, etc. One of the most interesting things that happened in answering this question, though, was in asking a different question very similar to what you just saw, right? Because we took a deep dive into statistics. I'm a huge number nerd, data guy through and through. And so with my wife sitting here saying, hey, let's watch Netflix, and I'm like, no, I've got MATLAB open, I'm going through these numbers, it's so exciting. One of the key findings we had was you can't decorrelate any of these because the structural design engineer considered things like climate, structure, traffic, etc. So they designed it for that, and then we want to turn around and use that to predict performance. It turns out to actually be a big mess. First phase of the project, we went through the literature review to find timing approaches. What we found were there were a couple approaches, but it all boiled down to a cost-benefit analysis. Right? Look at the cost of applying a pavement treatment, look at the benefits that you get, divide the two values, and there you go. You should get your timing. There's a few bits of research looking at material changes, but if you extrapolate out what that is, that fundamentally too is a cost-benefit analysis, right? Because you want to apply it whenever you maximize the benefits. What that looks like is to say, if I apply it too early, then I'm not going to get my maximum benefit. If I apply it too late, I'm not going to get my maximum benefit. I've got costs that change throughout time, so where is that low point? So we looked at several areas, and one of the first questions is, can we define a consistent set of costs? We pulled data in from 10 different states, and to answer that question, no, we can't define a consistent set of costs. The costs are all over the board. We were able to pull together a good set of guidance, but the way that Arkansas defines pavement costs, what they include is at one single lump sum, versus the way that Louisiana defines it versus the way that Tennessee defines it, just in their database to try to extract this data, the answer was no. How do we define benefits, right? And that, it depends, right? Are you concerned with ride quality? Are you concerned with cracking? Are you concerned with friction? So in order to define benefits, what we said is, okay, you can use whatever benefit you care about. So you notice here on the y-axis we have performance measure value. And then you just do a summation, right? You weight those all together. How do we consider uncertainties? We actually do a deep dive in the report, because as we started gathering the data from agencies, we found that y'all's data is pretty messy. And that means that if we're going to try to predict something, we can't give exactly 3.472 years to apply your pavement preservation treatment if the data is plus or minus 10 years, right? So how do we actually consider that? And then how do we compare costs and benefits? So we went into phase 2 of this project, and we said, okay, clearly one of the key questions to answer is, can we model the effects of preservation? Can we get that jump, and can we get that change in performance? During phase 1 of the project, we went through the literature, and the literature was all over the place. There are actually papers and technical reports that say, no, you can't get that data, or those data do not exist. There's a few journal articles written by the folks over there in the ivory tower that say, yes, these data do exist. So we said, okay, let's go out and see. Let's see what agencies are willing to give us data. Give us everything you have across the board. Can we model those? And we actually got a decent amount of data. You could see Kansas. They have a massive database of pavement condition, treatments, materials, all across the board. The next thing we had to say was, okay, well, lots of these data, they're not consistent. We want to actually try to work with a consistent set of values. So for example, if I'm looking at one agency's database and they have their climate split out into regions 1 through 4, and another state's database and they have their climate split out in regions 1 through 4, what does that mean, right? If one state's Alaska and the other state's Florida, it doesn't really mean a lot. So we looked as part of this research, and we developed a consistent set of features just in terms of subgrade soil and climate. So we were able to actually pull for the LTPP stores the MERA climate data now, the good old NASA data. And we actually developed values for every county in the US. The reason we did it for county level is because that's really kind of the finest grain that most agencies can give it to us. And we did the same for subgrade soil maps using a previous NCHRP project. I won't go into the details of making those maps. It was fun. The next thing we had to look at, like I said, was y'all's data is messy. How do I know what I'm looking at, if it actually received a treatment or not? So we got into the weeds with some detailed statistical analyses and artificial intelligence, like you saw, actually machine learning. We ended up developing an algorithm that predicted, okay, this agency gave me these data. They said nothing should have happened to these roads. Something should have happened to these roads. How much can I trust it? We go through the report how you can implement this. Actually, it's more simple than it sounds in your agency. But here I show a couple examples from the state of Kansas. Right, so in this case, you can see my IRI goes from 125 to 115 one year to the next. My rutting is 1/10 of an inch down to 5/100ths of an inch. And my transverse cracking, which is that equivalent cracking, stays the same. Did something happen to that pavement between the 2 years? I don't know. My IRI went down slightly. My rutting went down. Maybe they did some rut leveling. I don't know. So when we started looking at that, we developed an algorithm. And again, it's in the research report if you really want to dig into the weeds, or you can always email me. As you can tell, I love talking about this stuff. to figure out, okay, clearly there's some sections where there was no work done, right? 4% probability that anything was done there. Clearly there's some sections that something happened, right? Your cracking went down all the way, your rutting was reduced, and your IRI was reduced. The other thing we used this for was we were able to go through and extract from y'all's data a set of what we called control pavements. We defined those as pavements that should have been candidates for preservation but did not receive preservation. That's about as clear as the definition that you can actually apply to the databases without making way too many assumptions. And so we use this algorithm to then go through and filter out all those data. That way, for each state, what we ended up with is a set of preservation, right? These set of roads received thin overlays. These set of roads are control pavements, and then we can compare, okay, what happens if you apply the preservation versus what happens if you don't apply the preservation. This is basically the set of models that we were able to develop. When we look at, again, we're finding that initial condition jump, that initial change in condition, if there's anything, and differences in long-term performance as a function of whatever performance measure you care about. Do you care about IRI, rutting, transverse cracking, fatigue cracking, or non-wheel path longitudinal cracking? You can see we didn't get models for everything. Clearly the data do not exist for everything. But we were able to get a decent set of models. We talked to, so Jason actually brought up earlier, Jason Dietz, actually brought up the fact that I'd be bringing some examples from the EDC4. And actually, we were able to pull these models and this model development into that EDC4 project and show how these models could clearly identify the when and where of pavement preservation. Some interesting features we noticed was that for some reason, across DOTs and the LTPP, there was transverse cracking left after you applied a chip seal. Again, and I'm not going to be shy about it. I'm an academic. I love pavements. I love pavement performance. But I'm also not a field guy, right? I've been in the field and seen chip seals laid. It still didn't make a lot of sense to me that you would have cracking after your chip seal. We pulled all the state data out and said, okay, well, the LTPP, because you have measurements within a month or two after these chip seals are applied, in some cases 5 or 6 months, but still. And we still see transverse cracking after the chip seal was applied. We boiled it down to try to figure out, okay, what factor is predicting that? And it turns out the strongest predictor is the quantity of low severity transverse cracking, which still made me scratch my head. So I stopped trying to answer that because our project was running out of budget. Another thing that we looked at, and again, we're looking at state and LTPP data here, is what do we do with negative growth rates? What do I mean by negative growth rates? I mean those pavement sections where if you look at the IRI in year 0 and you look at the IRI over 10 years, it looks like it's a self-healing pavement. The thing's getting smoother, right? That's the kind of pavement we actually want to build in general. You all would be out of jobs if that were the case. So what do we do with those negative growth rates? Well, I tend to get up and walk out of presentations now whenever I see people say, oh, well, we just throw those data out. It's not what you do. Here's my one plea for you all sitting in this room that are still awake. If you're sitting in a research meeting and somebody says, oh, well, we just threw the negative growth rates out, or we just threw the negative values out, please, that's not right. We're engineers here. I teach engineering now. I know what kind of rigorous process we go through to train engineers. You all are actually smart people. So just to have them say, oh, I threw those negative growth rates out, what that does is it actually significantly biases your model. So what do we do with that? Well, where do they come from? We have to figure that out. Like I said, here's where your data should be. The red dots are where, or the blue dots are where your data should be, right? We all expect IRI increases over time, cracking increases over time. You measure that data at a network level, and that's how much uncertainty you have, right, between the diamonds. Which means it's very possible, it's actually statistically likely if you get 100 pavements that a small number, but a number of them will actually look like this. So you're going to fit a negative line to it. Right? So once you understand where it comes from, then you can understand how you treat it. You don't throw it out. Right? You do some fancy statistical modeling that we're not going to talk about here. And get something that looks like this, where my measured data still shows quite a bit of negative growth rates, but I'm not predicting something that's negative. Again, we go through that in the report in detail. So let's look at what we found. I want to take a step back here and say that what we did is something called exploratory data analysis. we wanted to understand what are the factors behind pavement performance when it relates to preservation, and how does that affect timing? So some of these models that you'll see, you'll kind of scratch your head about a little bit. These models, without going into too much detail, these models are not optimized for predicting, right? They're meant to investigate the data and show how each of these factors affect timing so that we can go back and say, okay, your timing models need to look like this. So with that being said, here's a decent model. In my own time, I developed a really cool model that actually accounted for the fact that many pavements didn't start experiencing cracking. But that's what a decent model looks like. We did a sensitivity analysis to find out, okay, well, based on the statistical model, what's affecting these? And this was one of the interesting cases where we said, okay, this is a transverse cracking growth model following a chip seal, but it's most sensitive to your IRI before your chip seal's placed. We went back, spent quite a bit of time on this model just to verify that, and it's true. So that tells you, hey, there's something more fundamental, right? That tells you a pavement is a system. IRI, cracking, rutting, they're all a big concern. Of course, if you apply preservation here, this preservation indicator, you get a negative correlation, which just means your cracking growth rate goes down if you apply preservation, whereas if your IRI is higher, then your cracking growth rate goes up. And so it made sense. One of the other models we looked at is IRI following chip seal. So what you have here are two probability distributions. And we were excited because we validated results found in literature, right? So the black line here is a distribution if you have a control site, and the blue data and the blue line are a distribution if you have a chip seal site. Simply the way to look at that is the black line is further over here than the blue line, so if you apply the chip seal, you reduce your IRI growth rate. We also run into the case where we have poor pavements. And this is, again, poor fits, but it's still informative. And this is another case where you start to think, okay, well, I'm designing my pavement with IRI in mind. So if I'm using all the same factors that I designed my pavement for to turn around and predict the performance, should I expect a good fit or not? In theory, you shouldn't expect a good fit, because if you already considered it in your design, then considering it in your performance is redundant. We still get good information out of this in terms of saying your IRI growth rate following a chip seal is reduced. If you apply preservation, that's not as important as your subgrade resilient modulus, your IRI before your chip seal, or your freeze-thaw cycles. It still has an effect. The other thing we looked at is uncertainty. I'm not going to go into a deep dive. As you can see, if you look at the IRI growth, or the change in IRI, so this is the immediate change, as a function of the IRI before the overlay, there's all these data points that are scattered, right? So you would expect that if I apply a thin overlay on a pavement with 50 IRI, the pavement I get out is about 50 IRI. If I apply a thin overlay with a pavement with 100 IRI, then I reduce it by 30, so you get 70 out. But there's scatter everywhere. Y'all's data's a mess. So then we combined cost benefits. We didn't use just a simple cost divided by benefits. We didn't try to monetize the benefit. We used to show why you should combine the costs and benefits that way. It's less sensitive. Again, it's in the report. But getting to what does this mean for timing? The report we actually have, well, in the report and the guide that are both published online, we actually have several examples to say, okay, our report, we have 50 some odd pages of models and statistics and model development. Go through that chapter. It's fun and exciting. But if you kind of want to skip through to see where the pictures are, we got a bunch of pictures. This is a couple of the examples. On your left, you can see the case of a no preservation versus a chip seal applied for transverse cracking and IRI. Like I told you, your IRI, in this case, you assume you apply it in year 0. Your IRI, you don't get an immediate change. Your transverse cracking, you do get an immediate change, but you get a reduced growth rate. On this side, we have an overlay applied, and you're assuming you apply it in year 0. Right? And you can see that in some cases the models look a little too linear. That's because, again, these models weren't optimized for prediction, although they can be used for prediction. If you look at that as well as the cost, you get plots that look like this. If I look at the benefit that I get out of applying the chip seal, again, from the left side, I could see that my benefit is maximized if I apply it in year 6. The blue lines there are the uncertainty, so massive amounts of uncertainty, but they still give you good information. The information I get out of this is, hey, maybe I actually need to rerun this analysis 4 years in the future or 2 years in the future when I'm more certain about my data. In this case, costs are also uncertain. Thin overlay costs more than your chip seal, so you could see that on the y-axis. Your thin overlay, you should apply it to maximize your benefits around 5 years in the future. So you combine them together, and it says, okay, well, if you want to apply your overlay value, it's around year 5. Your chip seal is around year 6. But again, these are example analyses because what I showed you earlier was depending on how you define your performance, what performance measure you use, how you weight the various performance measures, do I care more about cracking, rutting, or IRI, then it depends on how that shifts. The other thing that we see is when you look at the overlay being applied in year 5, it's driven primarily by the benefits that you get from the immediate change in condition, whereas applying the chip seal is mostly influenced by cost and the immediate change in your transverse cracking, but also the long-term change in your performance. The timing of pavement preservation fundamentally depends on what performance measure you care about, whether that specific treatment affects both the jump and the change in performance, or only one. In theory, it would be only one. If it affected nothing, then you're wasting your money. So what we said is, okay, the answer is not always to apply preservation right now. Sometimes, if the benefits come from that immediate jump, wait till the future to apply it. On the other hand, if the benefits come from the change in performance, like we saw with the IRI growth here, then maybe it is to apply it right now. Again, if you care about IRI and that's your main change in performance. Because we brought you here when it's still kind of cold outside, I'll leave you with a picture of Menorca. Say, do you have any questions?
Thank you for presentation, James. But the question that I have, so you came up with these models, but have you incorporated the life of the treatment itself into your model? So let's say for chip seals, for example, nationwide average is 5 years, right? So chip seal, and one of the most common distresses we have with chip seals is raveling, aggregate loss. Then within, and some states report even 3 years, that failure of chip seals. Then all of the levels, that performance levels, cracking or right quality at first, will be significantly low. So how do you account for that in the model?
So your question is, how do I account for the life of the treatment in my model? My answer to you is to refer to the previous presenter who so clearly asked, how do you define life? And it's a good question because that's actually what we started looking at. How do we define life? We looked at literature. There was some literature in Indiana, for example, that said, okay, your microsurfacing, and I know the researchers, by the way, great researchers. They said your microsurfacing can extend your rutting life by 15 years. We said, holy cow, that's a huge number. And then there was research that we pulled out, and we actually showed these comparisons in this report, where it's okay, microsurfacing extends your rutting life by 5 years. It's like, okay, maybe that's more reasonable. We don't know. There's not a clear definition for what pavement life is at all. We had a federal highway project report published in 2016 where they said, okay, we want to move to the remaining service interval life, and I was on the research team. And for maybe the first year on that research team, I was kind of the voice that said, what are you guys talking about, remaining service interval? It's just remaining service life repackaged. And then it fundamentally clicked, right? Everything that Dr. Hall was talking about earlier fundamentally clicked and said, oh, nobody defines life the same way. Nobody, yeah, there is a definition for life, but nobody uses that. Everybody says, oh, this treatment lasts 7 years. Okay, so I'm going to go put this treatment down and I'll come back and see it in 7 years. I mean, it's not the way it's clearly defined. The way that we looked at the life of the treatment is fundamentally built into the performance models. There's a nonlinearity in there that shows clearly where, we do go through it in the report, and I don't want to take too much time, but there's a nonlinearity in there that clearly shows an inflection point in some models, not all models, where it seems that you stop, it can be interpreted as you stop receiving benefits from that treatment, right? Where the growth rate is where it should have been had you not applied the treatment, even though your condition's better because you saw that immediate jump.
My question to you and also the previous presenter, it may not be a question. My question is, say, we do the pavement designs in typical, say 30 years and then do the analysis for 50 years. And we all know the pavement preservation improve the ride quality, smoothness, and friction. But if we do regular intervals, say ideal condition, every 7 years, that does not mean that that pavement will last 50 years, meaning that we are doing. So my question is, when you think that we need to incorporate all or consider the structural thing too, not only doing the pavement preservation, say.
Yeah, and that's a great question. I'm a big believer in that big device that's driving around the country right now, the TSD. I don't know. I'm still shocked to see how divided that DOT offices are. I'm still, I guess a young PhD, so in my mind I think everybody communicates well. But raise your hand if you know about the TSD. Okay, a decent amount of people in here. I'm a big proponent of, if we're going to go out and measure the functional condition of the roads, we also need to have some sort of structural measure. Because all too often we're seeing these chip seals, and I'm going to use this language. We're going to go out and we're going to say, okay, these chip seals should last for 6 or 7 years. But then I apply it on a pavement that's not structurally adequate, and it lasts for a year. Right? And again, being loose with my terminology there with life. So we need some sort of structural evaluation included. As a matter of fact, the Federal Highway EDC webinar that we gave last week, we clearly said that. We said you need to know not only the functional condition of your road, but if you're really going to make a good decision, you need to know the structural condition of your road. Structural condition of the road, you could talk to the colleague next to you, because Virginia DOT has a very good approach for determining the structural condition of the road. I am going to brag a little bit. It was my master's thesis. But basically where it says, okay, we consider traffic, we consider all these factors in saying whether or not this is structurally adequate.
I think it's a really important question, and I think one of the things that I have seen, some states do this better than other states. Traffic is a place that we really fall down sometimes, especially at the network level. There are many states that the best you can do is once every 2 or 3 years updated traffic map, which may or may not include a lot of data. So your question, when do we apply the structural, has to be a combination of condition and expected traffic. If you have we sometimes want to assume that for our major highways, traffic is always going to grow. Maybe it doesn't, maybe it does. But the key is, does your asset management system actually have decent traffic data in it so you can make that decision? I mean, if you're still within the parameters of the original design, then your pavement should, structurally your pavement should be okay. But if you're expecting big growth in the traffic, or if the traffic has shown big growth beyond what the original structural design considered, then now you probably ought to be considering a structural fix for that and add structural capacity. That's a fundamental question. Pavement preservation versus adding structural capacity. Why do you add structural capacity? It's a combination of structural condition and expected traffic. Does your asset management system actually have decent traffic data? It depends, really, where you are at.
So Brian Diefendorfer and I had this conversation actually 2 weeks ago, right? So the question was, I did a report where I said we had actually VDOT run out and they thumped their pavement every 0.2 of a mile, right, with the FWD, all of their interstates, which is a pretty impressive undertaking. And we came back several years later and said, okay, how do we actually use these data? So the conversation that Brian and I had, because he reached out and said, okay, well, what about the structural condition of I-81 here? And I said, okay, well, remember that in phase 2, and I'm going to follow up exactly with what Dr. Hall said. I said phase 2, which is the implementation of this, one of the biggest efforts we had was trying to refine the traffic data, because the structural model that I presented to them actually does account for traffic data, and it was actually fairly sensitive to traffic data. So please keep in mind that as you go forward, if you have better traffic data, please include it in the models, however it is here. With that being said, yes, there are several sections out on I-81 there that we would call structurally, not structurally adequate for potentially receiving preservation. And there were several sections that, based on the historical data we had, right? We had 2006 FWD data, and then by the time we went to the second phase, we had up to 2013 functional condition data. So we were actually, it wasn't something that we were projecting forward to say maybe this would work. It was actually something that we had several years of performance data to then turn around and validate it with. that is one of the conclusions that we came up with. Hey, there are areas maybe you don't want to apply preservation, you need a structural treatment there, with the caveat that not only traffic, but subgrade resilient modulus data, you really needed better information on that too, because again, pavements are systems. You got a soil, you got something on top of the soil, and you got something driving on top of it. You can't ignore any of that. And by the way, you've got the sun beating down on it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.